Hello.
Sir. Hello, good evening.
Hello.
Hello, your screen is visible now.
Okay. Audible, visibility, everything okay?
Yes, sir.
Okay. So let me. So we're going to start. We had started looking at what is called a basis for the vector space in Rn. So let us just recall what we are looking at. So we looked at some examples of linear span of vectors, and we saw that sometimes we cannot drop some vectors. So there is a minimal set of vectors whose linear spans give the space. So we made a definition there that a vector space inside Rn. So they are all subsets of Rn. Just a minute, let me highlight. Yeah. So a minimal set of generators, you can call it as a basis. The minimal generators means the linear span of those vectors will give every vector. So this is the notation we use for that. Okay, right. So the claim is that for V which is not equal to 0, that means it has at least one non-zero element. If you look at the set V1, V2, Vn of vectors in V, then the following statements are equivalent. V is a basis of V, that means it is a minimal set of generators. Every element of V has a unique representation as a linear combination of elements of V. See, when you say it is a minimal set of generators, so generators means every vector in V is a linear combination, right? And definition says it is a minimal set with that property. And property 2 says this is equivalent to saying that every vector is representable as a linear combination and it is unique. So that is the two are equivalent. And the third version is that these vectors in B generate V. That means everything is a linear combination, right? And instead of unique, we are putting a condition now that if a linear combination of them is 0, then each one of them is 0. So this is the third equivalent way of describing. And the fourth is it is a maximal subset of, it should be B, not V, it should be of B, uh, which says that every element has a unique representation in B. So these are four different ways of describing what is a basis. One is in terms of minimal set of generators. Other is saying that every vector in V is a linear combination but a unique representation. And this is that there is a representation of 0 is unique, right? This is alpha vi, alpha I vi equal to 0. The representation of 0 is unique, then everything also becomes unique. And it is a maximal set with these properties, that 0 has a unique representation. So these are four different ways of characterizing a basis. I'm sure all of you must have come across this. For example, let us look at proof of some of them. Okay. Okay. So let me just give a short outline of the proof of say one implies one is equivalent to two. Okay. So let us say so. So one says that uh, the linear span of B is equal to V and B is minimal. And 2 says uh, every element of V has a unique representation. So let us write. So for every vector B belonging to V, B is equal to sigma alpha I Vi. B is V1, V2, Vk. And has a representation, and alpha is unique. Okay. So let us say how does one imply two, right? So if the representation is not unique, so in case V is equal to sigma alpha I Vi, say I equal to 1 to k, also equal to sigma beta I I equal to 1 to k. Suppose there are two representations possible, so that will imply that okay, uh, alpha i's are unique, right? So if not, then alpha I minus beta I v I summation I equal to 1 to n is equal to 0. And if it is not, in case where alpha, not all alpha i's are equal to beta i's, then one of them is different. Say the first one, uh, in that case, that will imply, so that implies, say for example, say alpha 1 is not, not all are equal. So alpha 1 is not equal to beta 1. So in that case, that is not 0. So I can write V1 equal to sigma I equal to 2 to n alpha I minus beta I divided by alpha 1 minus beta 1, because that is not 0, Vi. So that means this V, that means V is a linear combination of V2, Vk, and that means that implies that V is not minimal, because I can drop V1, I can drop V1 and then the remaining will be good enough, because V1 is a linear combination of the others, so it's not minimal. So uh, contradicting one. So not 2 implies not 1, so that hence 1 implies 2. And I think all the proofs are similar small manipulations only. So I think I will leave this proof that 1 is equivalent to 2, 2 is equivalent to 3, and 3 is equivalent to 4. And most of you must have gone through these proofs in your courses in linear, first courses in linear algebra. So I will skip the proofs of the remaining, and I will strongly says that please go through these proofs yourself without looking at anything. Just look at the definitions and try to work out the proofs. That way you will learn more about the proofs rather than reading a book or something. Okay, so all these four are equivalent, and If any one of the conditions is satisfied, we say that we have got a basis for the underlying vector space. And this condition that sigma alpha I vi equal to 0 implies each alpha I is equal to 0 is given a name. One says these vectors are linearly independent. So with that terminology, B is a minimal set of generators, right? Every vector has a unique representation, and that is equivalent to saying that it generates and the set is linearly independent. So it's a linearly independent set of generators. That is the second way of looking at it. And it's a maximal linearly independent subset of that set. That is another way of looking at it. So in terms of the terminology of independence and dependence. So these are the ways of looking at it. B is linearly independent set and it generates, okay, and or it is a maximal linearly independent set, and equivalently it is B is a minimal set of generators. So all of these are equivalent definitions of saying something is a vector space. Why one question one can ask, why does one prove such kind of a theorem where various things are equivalent, kind of a thing. The reason is that in different situations, different things are easy to prove. So sometimes we may be able to show that a set of vectors generates and is uh, linearly independent, or we may be able to say it generates and it is a minimal. So depending on the situation, one form or the other is useful, and all these equivalent ways of describing the same thing are very useful and very important things. For example, in the course in analysis, in a course in analysis, you would have come across something like looking at the motion of limits. They are saying that a sequence of real numbers is convergent if and only if it is Cauchy. So both are equivalent ways of saying a sequence is convergent. But sometimes it is easier to prove a sequence is Cauchy and you are not really interested in knowing the limit. So then that proving Cauchiness is good enough and is useful. But sometimes you have to find the limit, then you have to sort of say find a value so that the sequence converges to that value. So these are equivalent ways of describing in mathematics various things which are useful, and we should stress it to our students that these are important things in the topic. So here is a theorem which I would like to probably stress on it. Let S and T be two non-empty finite subsets of a vector space V. Says that T is a subset of S. T is a subset of, this is a span. T is a subset of the span of S. Okay. So this square bracket is just saying that T is inside the span. So linear span of S is also written as uh, square bracket. And suppose second condition is that T has more number of elements than S. S and T are two sets. Suppose T has got more number of elements than S, and the span of T is inside S, then the claim is T is a linearly dependent set. And what is a linearly dependent set? Which is not independent is said to be linearly dependent set. Okay, right. So let us look at a proof of this. So let us take the two sets to be S to be equal to V1, V2, Vn, and T to be equal to W1, W2, Wm. Okay, right. So the assumption two says that M is bigger than or equal to N. M is strictly bigger than N. Okay. So that is the assumption given to us. And second thing is given is that the T lies inside the span of S. Okay. So now let us, because each Wi T is inside the span of S, so each Wi must be a linear combination of elements of S. So there will be scalars alpha j I such that each each wi is a linear combination of alpha ij vj j going from 1 to n. Okay, that is because of the condition given that t is inside the span of S, right? So this we know, each wi is this. Now let us look at arbitrary scalars beta 1, beta 2, beta m. Okay, look at the scalars I is from 1 to m. So look at scalars beta y, beta m. Say that this and form the linear combination sigma beta I wi, I equal to 1 to m. Then I can put this value here. Just a minute, let me switch on my battery. I think it's getting low. Yeah, good. So it's on, yeah, it's on charging. Okay, good. So each wi is a linear combination of Vj because T is inside the span of S. And now for arbitrary scalars, form this linear combination sigma beta I wi, I equal to 1 to m. Now each wi has got that linear combination, so put that value here and interchange the two sums. They are finite sums, so we can interchange them. So once you interchange, you get j equal to 1 to n, summation alpha ji beta I Vj, right? We have not done anything except that each wi were represented like this, and for arbitrary collection of scalars we have got this. Now look at this inner bracket that I can think as a system of linear equations with the alpha ij as the matrix, coefficient matrix, and beta ij to be the unknowns. So since m is bigger than n, so this alpha ij, okay, if I look at that, then j is from 1 to n and I is from 1 to m, and I'm given m is bigger than n. So this is a system of equations where number of equations is more than the number of variables. So m is bigger than n. So I can always find a non-zero solution for it. So this is the result coming from the system of linear equations, that you got a system of linear equations where the m is bigger than n. Okay, then there is always a non-trivial solution. So pick up for each beta, for every j, pick up a non-trivial solution. Okay, such that alpha ij beta I is equal to 0. So select those beta i's and put these values back there in this equation. Then you will get sigma beta I wi is equal to 0. And just now we said that these not all these scalars are equal to 0 because it is a non-trivial solution. So that means the vectors w1, w2, m are linearly dependent set because we have got a linear combination which is 0 and not all the coefficients involved are 0. So this is purely a simple result based on the fact that for a system of linear equations, a non-zero homogeneous system of linear equations, Ax is equal to 0. Okay, we have a non-trivial solution whenever the number of m is bigger than n. If Ax is equal to 0, if it is a m cross n system, homogeneous system, and m is strictly bigger than n, then there is a non-zero solution for it, right? Because the rank will be strictly less. So that is an obvious fact, and that fact is used to prove this. That so this is a very simple but very interesting result. It says that, sorry, what is the result is if T and S are two finite subsets, and if T is inside the span of this, and T has more number of elements than T is linearly dependent. So this gives us some nice consequences. The first consequence is if S and T are two non-empty subsets of vector space with the following properties. T is inside S and T is linearly independent. So T is a linearly independent now. We are given then T must have less number of elements than that of S. And the number of elements of T, if T is a linearly independent subset of S or the span of S, then T must have less number of elements than that of S. That is a very good result. We'll see some consequences of that. One immediate consequence of this is the following, that uh, if V is has a basis consisting of n elements, then any set having more than n elements must be linearly dependent. Whatever they may be, there may not be any relation between them. Okay, so that is one corollary, and obviously the second corollary is the one which we are trying to hit, that any two bases of a vector space has got same number of elements, because if there are two bases T and S, right, of the same vector space, then T is inside the span of S, S is inside the span of T, and both are linearly independent. So the number of elements of T must be less than or equal to number of elements of S, and other way around, number of elements of S must be less than or equal to number of elements of T, and that says that any two bases of a vector space will have the same number of elements, right? So the bases could be, there could be many bases, but the number of elements in that basis in each base will be same. So that gives us a very simple way of looking at what is called the dimension of a vector space. So we say a vector space has got dimension whatever that we want to call it, n or m, depending upon there is a basis consisting of, there exists a basis of that number of elements. Okay, there are simply the number of elements in a basis of a vector space is called dimension. And one can ask now various things. For example, does every vector space have a basis? Here, vector spaces are all subsets of Rn. Okay, we know for Rn we can give a basis, the standard basis we can give 1000 and 0100 and so on, one at the ith place. That is a linearly independent set, and every vector is a linear combination of that. So that is a basis, right? So that gives us a for the so every subspace of will have a dimension less than or equal to n if n is the, it is n vectors, there is a subset of Rn. Okay. Uh, how do you show the basis exists? Because Rn has a basis number of elements. So what we can do is we can given any uh, subset V inside S, what we can do, there are two ways of doing it. One is try to locate a set of generators for V. Okay, that means some subset B of V, say that L of B is equal to V, and then try to remove from them the ones which are not required, which are one by one. You can look whether that if I remove it, does it become is the given set linearly dependent or not? If it's dependent, then one of them must be a linear combination of the remaining. One can drop that and go on making it a minimal set of generators. So that is one way of doing it. The other is you start with a non-zero vector in that vector space V, which is a subset of Rn. So because if it is zero, then there is nothing to prove. So if it is a non-zero vector spaces for the time being, we are all are subsets of Rn. Keep that in mind. Then there is a non-zero vector in that. So start with that. Okay, look at the span of that. The span of that may not be equal to the whole of that space. So there must be a vector. If it is not, there is a vector outside it. So we can add that and look at the two element set and then generate this. Okay. because because that is not a linear combination of any one of them, so that must be linearly independent. So one way is expanding a set to a linearly independent set of generators, and the other is shrinking a set of generators to a minimal set to get a basis. So these are two different ways of showing for in our scenario the basis. There exists a basis for a vector space. Okay. Let us just, I think at this stage, probably let me just ask a question to see how many are listening or how many are on the portal. What are all possible subspaces? What are all vector spaces inside R3? So that is a question. Please put your answers in the chat box. I want you to describe them geometrically. Geometrically describe all subspaces of all vector spaces in R3. So please put your answers in the chat box, and it will kindly help us in locating if somebody has an answer to that. So what I am looking at. So let me write the question if you want to. So V contained in R3, V a vector space. Question or describe geometrically. I think somebody has put a remark. Planes. Somebody said planes and lines passing through origin. So anybody else? Is that yes? So let me look at it. Devanshu Biswas says lines passing through origin, planes passing through origin. These are okay. And Jaya Kumar says empty set. Wow, great. So both these need now discussion. Lines passing through origin. So let me first go to Jaya Kumar. Are you there? Jaya Kumar, name is slightly long, so I cannot pronounce it very well. Kudalingam. Okay. Can empty set be a vector space in? So here is a question. Probably we should explore. Can I say V is equal to empty set? Okay. I think let me pick up somebody and start a discussion. Anand Soni, are you there? Anand Soni. Dilpreet, can you unmute his mic? Anand Soni,
Okay.
if possible.
Yeah, yeah. Okay.
Anand Soni, are you able to listen?
Now, now everyone can unmute themselves.
Anand Soni, no? No response?
No.
Okay, Arup Datta, are you there?
Yes, sir.
So can B be equal to empty set?
No, sir. Zero vector is not in empty set.
Right. So as soon as you look at a vector space, we said that it should have the property that for every scalar alpha and every vector v in V, alpha v should be inside it. So if you choose alpha to be equal to 0, then the 0 has to be inside it, every vector space. Okay, so that is not correct. And would you like to continue and tell me, Arup, whether what are all subspaces of R3?
Sir, plane origin, line passing through origin, and the origin itself, the set containing only origin. That means 0, 0, 0.
So are these the only subspaces? You have given me some examples. The zero vector alone itself, a straight line passing through origin, and a plane containing the origin. These are examples of subspaces. You said, right?
Yes,
So,
sir. And R3 itself.
yeah, are these the only ones? Is there anything else other than these? How do you ensure that?
Sir, I think,
Yeah, you need to think. You see, when you say describe all, you can give me some examples, but how do you ensure that these are the only ones? Okay. Yeah, I
yes,
think
sir.
that anyone else would like to uh, say something about Arnab. Is Arnab there?
Yes, sir.
Yeah, Arnab, can you say that the only subspaces or only vector spaces inside R3 are the trivial ones, namely 0 or the whole R3, or a line passing through origin or a plane passing through origin? That these are the only examples. You can't find anything else. What could be a reason for that?
Because the zero vector has to be there in the subspace.
No, all of them have 0. So I'm not doubting that these are examples of vector spaces, but these are
No,
the only ones. There is nothing else. How do I ensure that? Okay. So I think is Khyati there? Khyati Sharma? Hello. Is
Yes,
Khyati
sir.
Sharma there?
Yes, sir.
Yeah.
I am also thinking these are the only subspaces of R3, but I am thinking how to prove this.
How to prove this? Good.
Yes.
So, Dilpreet, you can take this as a question for the discussion in the tutorial session tomorrow, or day after tomorrow, whenever it is. Okay, tomorrow. So that these are the only vector spaces inside R3. How do you ensure these are the only? Actually, I have already answered this question, so let me not spend too much time on this. Okay.
Okay.
Actually, the answer lies in that slide. Just now, I'm showing you. Okay. So let us go over to a bit more uh, to something more. So existence of basis, I have already discussed that. So let me not spend time on that. Uh, uh, I think I'll skip these ones because, yeah, here is something important I should discuss. So let us come back to matrices. For a matrix A, you can write its rows as here in this slide is A1, A2, Am are the rows of the matrix. So they are vectors. If A is M cross M, so if A is M cross N, then here let us write rows of this. I'm looking at the set of rows. So let me delete this. So let us look at okay. Okay, let me take R1, R2. How many rows will be there if it is m cross n? M rows and n columns, right? So m. This will be A is, these are the rows. So forget about A is a matrix with these rows. Okay. So A is a matrix with the rows. We want to write is R1, R2, Rm. And look at the vectors, as I said, this is a subset of each vector has got n components, so this is a subset of Rn. Okay, so look at this and look at the span of this. So look at the span of the row vectors of a matrix. That will be called as VR. So span of the rows, and that is subset of subspace of Rm. So this is given a name. It is an important. This is an important space. It is called the row space, and dimension of the row space is called the rank of row rank of the matrix. So for every matrix, look at the rows, look at the span. That is a subspace. Call it as of Rn. Call it as a row space of A, and dimension of that is called the row rank of A. Similarly, you can look at the column vectors and span the columns. Look at the each column. Each column will be a vector having entries will be, it will be a point in Rm. So you can span that space by the column vectors and call that as a column space of it. And dimension of the column space is called the column rank. Okay, so there are two numbers attached to it, the row rank and the column rank. And we are going to describe these spaces and the relation between the row rank, column rank, and so on. So here is the first observation. So row rank, column rank, okay, doesn't matter. So the first observation, look at the first theorem. It says that if A is m cross n matrix and B is obtained from A by row operations, elementary row operation, then the rank does not change. Then the rank of A is same as the rank of B. Why is that? Because the row space is spanned by the row vectors, and elementary row operations, what they do, either it multiplies a row with something, or interchanging the row, one row with another. That is only reordering how the rows are written. Okay, and the third is multiplying by a scalar, okay, or adding one row to another. So let me just probably write what we are saying. So if you have a the row space, so row of space of A is the span of the row vectors. So let me call it as R1, R2, Rm. Okay. So when if I make a change, a row operation on A, what I will be doing? Either I will be adding one row to another. So then this set will change to R1. Say for example, I add R1 to R2. So it will be R2 plus R1, Rm. Right? There only is a linear combination of these vectors only, and the span is all linear combination. So this is equal to this. It does not change. Similarly, if I multiply, so if I take R1 and say alpha times so R2 something and Rm, then the span of this is also equal to the same thing. Okay, and interchange means what? Interchange means will be, instead of writing R1 R2, you will be writing R2 R1. But as I said, it does not matter. So that So this, I'm just trying to make it more visible, the fact that row operations do not change the rank. So finally, that should mean the rank of the matrix A is same as the rank of any one of its row echelon form or the reduced row echelon form. So rank of A is same as rank of A tilde, right? Where A tilde is a row echelon form of it. So that is one observation. The second observation we want to say is that if you look at row operations and look at the column space, that may change, but the rank of that does not change. So what we want to say is, if a matrix A, you change it by elementary row operation to a matrix B, then the rank of A is same as the rank of B. Okay. Why is that? Let me probably write that instead of just showing a slide. So here is a matrix A, okay, with rows as R1, Rm, and if you write it as columns, it is C1, Cn. Okay. So for the column rank, I have to look at the column space. So I have to look at the how many of these generate. Okay. So let us say, so suppose among all these columns, uh, some of the columns are independent. So let us say Ci1, Ci2, Cin are independent. Okay. Let us take a linear combination of them. Okay. So I have got the column C1, C2, Cn, and I'm supposing that these columns are, and let us write A tilde to be C1 tilde, C2 tilde, Cn tilde. This is the row echelon form of A. So A tilde. Okay. Now, my claim is that if some columns are independent here, the corresponding columns are also independent here. Okay. So let us write that. So let us take a linear combination. So let alpha I1. So I assumed, okay, this is, I should have said take independence there. So let me just modify that. So suppose Ci tilde. So let me write what I am trying to prove, so that you are clear what about the proof. So let me just modify my slide a bit, so that so this is, so let A tilde, the columns of A tilde are given here, where A is the given matrix and A tilde is the row echelon form of A. So suppose, so now let us write, so suppose in the this one, Ci1 tilde, Ci2 tilde, Cik tilde are linearly independent. So suppose out of the columns of A tilde, these ones are linearly independent. Okay. The claim uh, that Ci1, Ci2, Cik are linearly independent. These are the columns of the original one A. These are the same numbered columns in A. So what we are saying is, if some columns are linearly independent in A tilde, the corresponding columns are also independent in A, because let us take a linear combination. So alpha I1 Ci1 plus alpha Ik Cik equal to 0, right? I should show that each one of them is equal to 0. But look at this means what? Let us add everything. So I can write as sigma alpha I Ci I equal to 1 to how many columns are there in A? N. I can write it. This is equal to 0, where alpha, okay, let me write J here, and where alpha for J equal to for where alpha J is equal to 0 if J is not equal to I k. If is not one of these, then put it equal to 0. I'm saying add to this 0 times C1 plus 0 times the missing ones you add, and this is equal to 0. Okay, and that means if I look at the columns C1, C2, Cn and apply it to alpha 1 to alpha n, that is equal to 0. So this is the realization you should have. The saying a linear combination of the columns is equal to 0 is same as you take the matrix with that columns that apply to alpha 1 alpha n is equal to 0. That means that alpha 1 alpha n is a solution, right, of homogeneous system, right? This is a solution of the homogeneous system, right? And and that will imply that this is also a solution for the row echelon form. So that will give you, if I could go back, so that will say that sigma alpha I, alpha I1 C1 tilde plus alpha I k ck tilde, no sorry, no tilde for alpha is equal to 0. I go back now, okay, because this is a solution here for A applied to alpha is equal to 0 for the homogeneous system. So correspondingly for the row echelon form also that should be a solution. And now forget about the 0 terms, and this is equal to 0, and that should imply, because these were linearly independent, right? So these were linearly independent here. We said we start with linearly independent, so that implies that alpha i's are equal to 0 for every alpha ij is 0 for every j. So that implies that ci1 cij are linearly independent. So you can try to write a proof yourself. There's nothing very complicated in the proof. What we are saying is, if in a matrix A these are the columns and these are the columns of A tilde, then whatever is independent here, that remains independent here, and whatever is dependent here remains dependent here. Okay, so independence and dependence of columns do not change when you apply elementary row operations. Okay, and here is a second observation about the row echelon form. So let us write A tilde. We had the row echelon form C1 tilde, Cn tilde. Okay, these are the columns of a tilde. Now look at the claim is the pivotal columns See, there were the pivots. Okay, so what were the pivots? So let us write, remember that p1 less than p2 less than pr be the pivotal columns. So what is the property of the pivotal columns? So in the pivotal columns, so if I write that matrix, okay, and write the pivotal column pi, so that says it is 0 and 1 and 0 here, and this is the ith this is the ith row and ith column. So that is the first non-zero entry for the ith row. For the ith row, the first non-zero entry is here, and that is equal to 1. Everything else is 0. 0 on this side and 0 below also. Okay. Now, so here is P1, P2, and Pn, those pivotal columns. Okay. And the claim is that these pivotal columns are pivotal columns are linearly independent. They are linearly independent, right? That is okay, because when you take alpha I, the pivotal column pi, so that will appear here alpha I, and if that is equal to 0, each alpha I must be equal to 0. So there is obvious thing that they are linearly independent. And second, each column is okay. You can write each column is a linear combination of these pivotal columns. So if you take any other column, then I can write that as a linear combination of these pivotal columns. That also is obvious from the way we have described. So if I take a column, these are all 0. On this side, that scalar times whichever number is coming here in this column, that times this column plus the other ones will give you a linear combination. So what does this imply? This implies that the number of linearly independent columns in A is equal to number of pivots. And the pivotal columns are the ones which will pivotal columns that I think we have already written are linearly independent. Okay. And let us also make one more observation, namely look at the row space. So that looks like R1, Rn, and R, say R and 0 here. Okay. So this is okay. I think I should write here. Okay. Is it clear that these row vectors are R1 tilde, R2 tilde, R tilde in the row equivalent form? This is the row equivalent form of A, are linearly independent. They are linearly independent, right? Because in that row, everything is, say in this row, okay, if you look at that row, it is everything is 0, and here is 1 at the pivotal column P1 in the row 1. In row 2, everything is 0 except at P2. So that is 0 and that is 1. So if I have alpha I r I sigma equal to 0, I equal to 1 to r, right? Then I can look at that component. P1th component of this equation will give you alpha P1 is equal to 0. Okay, and similarly alpha 1 P1th component will give you alpha 1 is equal to 0. The 2th component will give you alpha 2 is equal to 0, and so on. So a linear combination of the non-zero rows in the row equivalent form if it is equal to 0. Look at this is a vector equation, right? Array has got components. Look at the p1th component. That component is alpha 1 and okay, that is equal to 0, and because that sum is equal to 0 means that is equal to 0. So what we have shown from this is, I think all this I have shown. The row rank does not, row rank is the number of the row vectors or matrix A tilde form a basis of the row space. Just now we showed that they are linearly independent and equal to the number of R, the number of non-zero rows. They are linearly independent, and these are the only non-zero vectors. So the maximum linearly independent set. So that forms a basis for the row space. The pivotal columns of A form a basis for the column space of A, because we have shown that in the row equivalent form, the pivotal columns are linearly independent and they span the column space. And the column space remains independent, it remains unchanged, right? The independence remains unchanged under the row operations. Space, right? Columns may change, but the independence of whatever is independent in A remains independent. Those columns remain independent in A tilde. So you form a. So to pick up the independent columns of A, you just have to look at the pivotal columns of A, and that gives you the independent column. And these also have applications. Let me just give you quickly those applications of these things, which are from the computation point of view. So let us look at some applications. You are given some vectors v1, v2, vk. Okay, let us say they are vectors in Rn, and so this is a set S. S may be independent, may not be independent. So how to select a basis for the linear span of S? Yeah, I'm given a set of vectors. I want to find a basis for the span. They will span something, right? So I want to find a basis of it. So here is a method we can do. So construct a matrix A with these as the rows. So V1, V2, Vk. Construct these as the a matrix with these as the rows, okay, and change it to A tilde, which is a row equivalent form. So row equivalent form will look like some V1 tilde, V2 tilde, up to some VR tilde, and the remaining will be all 0. That is row equivalent form of A. So take the form the matrix with the given vectors as the row vectors, okay, as the row vectors. Reduce it to row equivalent form, you'll get non-zero rows. Then the claim, as we have seen just now, that the span of V1 tilde, VR tilde is equal to span of V1, Vk, the given one, the span of this, they are equal, and these are linearly independent. So they form a basis. So to find a basis for the span of a given set of vectors, form a matrix with these as the row vectors, reduce it to row equivalent form. The non-zero rows will give you a basis for the span of it. Okay. Your vectors would have changed, but you have gotten a basis. There is a second question application we would like to ask is following the same thing. Let us take S to be equal to V1, Vk, right? Just now we found a basis for it, but what I want is I want a basis out of these vectors. So find a basis of linear span of S from the given set. I want to pick up out of V1, V2, Vk the ones which are linearly independent and will give me the same span. So for that, the idea is to construct a matrix A. Now these should be the columns. So V1, Vk as the columns of that matrix. Okay, reduce it to row equivalent form. That will give you V1 tilde and Vk tilde, right? So, and out of these, pick pivotals. So P1, P2, PR are the pivots. So then VP1, VP2 in the original VP2, VPR is a basis for the linear span of V1, Vk. So there are two ways. Given a set of vectors V1, V2, Vk, if I want to find a basis of it, I'm not really interested in picking out of V1, V2, Vk the ones which are really independent in span. Then I just consider write A as a matrix with these as rows, reduce it to row equivalent form, then the non-zero rows will give me a uh, basis for the row space of A, and hence a basis for the linear span of S. If I want to pick out of it the ones which are linearly independent and give me the required thing, then I should write it as a column, as the columns, reduce it to row equivalent form, and pick up note down the pivotal columns P1, P2, PR, and the corresponding VP1, VPR will give me a basis for this. So I think,
Professor,
yeah, I think we have come to the right stage of stopping for the first part of the lecture today. So I have finished describing basis, dimension, and I have also finished uh, describing the null space, the row space, and actually I have also proved what is called the vac nullity theorem. I did not write it because if n is the number of columns, r is the rank, that is the same as the number of row rank is same as the column rank. So the rank r, right, the nullity, the dimension of the null space is plus rank plus nullity is equal to n, right? That also has been proved. I think it's okay. Probably you should observe that because dimension of the column space is same as dimension of the row space. Both are equal to r, and the nullity, the columns n minus r columns in the row rank in the row equivalent form are obtained from the others by linear combinations. Every other one is a linear combination. So that says precisely that the dimension of the null space is equal to n minus r. So I think I'll stop here for break of 15 minutes.
yes, Professor. So
Okay, fine.
now there is a break for 15 minutes. It's 6:06. So we'll start at 6:20. Is that fine?
Anytime you'd say.
Okay, we can take break of 15 minutes.
Yeah, sure.
Okay, so we'll start lecture 4 at 6.
Okay,
So I
fine.
am keeping this meeting on. So you can join at 6:20. It's up to you.
It's okay. Thank
Okay.
you.
Thank you, Professor Rana. Okay, we'll begin at 6:20 for lecture 4.
Yeah, sure.